So, welcome to the third tutorial for the course Basic Linear Algebra. I'll be covering content related to third week of the course, whatever is being taught by Professor Indra Kumar Rana. I'm Pintu Kumar. I'm a PhD scholar at IUR IT Bombay. So, today I plan to cover linear independence and rank nullity theorem. So, if you guys have any doubt at any point, you can either unmute yourself and speak, or you can just type it in the chat box. Both language, Hindi and English, can be used for interaction, whichever you are more comfortable. Okay. So, like till now, you might know that this course is all about vectors. And so, first of all, we'll talk about linear independence of vector. And if you want to look at some resource for this content, then Linear Algebra by Fredberg can be a good resource to look at. So chapter 1 and 2 can be referred for whatever we are discussing today. So you'll get linear independence somewhere in chapter 1 and rank nullity theorem somewhere in chapter 2. Okay. So before we go to linear independence and we try solving some problems related to that, let's first of all see what linear dependent or independence is, so that all of us are on same page. Okay. So we talk about linear dependence or independence of a set. Okay, set of vectors. We talk about linear independence or dependence of set of vectors. So a subset S, let's say S has your vectors v1, v2, vn. Okay, or let's use the same notation that these people have used. So let's say you have vectors u1, u2, un. So you call them linearly dependent. I'm talking about linear dependence right now, not independence. So you call them linear dependent if you have some scalars as a1, a2, a3, an such that all of them are non-zero. So some of them can be 0, but you need that at least one of them should be non-zero. Okay, so at least one of these ai's should be non-zero. And if you can write this u1, u2 as a linear combination using these scalars so that they sum up to 0, then this kind of then this set of vectors is called linearly dependent vectors. Okay, so I'll repeat myself. So if you have u1, u2, un vectors, okay, and you get a1, a2, a3, an, these are scalars, and you can write a1 times u1 plus a2 times u2 so on till an times un as 0, such that if not all ans are 0 for all n, then you can say that your u1, u2, un are linearly dependent. Okay, then they are linearly dependent. I'll take a very simple example right now. Let's take a two-dimensional vector only. Let's say we have u1 is equal to 1, 1. Okay, and you have u2 is equal to minus 2 comma minus 2. Okay, if you now carefully look and take a1 is equal to minus 2 and u2 is equal to 1, then what you can write, a1 times u1 plus a2 times u2. What is this? This is minus 2 into 1, 1 plus 1 into minus 2 minus 2, which gives you 0 comma 0, right? So over here, if you look at this set of vectors u1 comma u2, this set is linearly dependent. Okay, I'll give you an example where this is not linearly dependent also. Then we'll move to more concrete examples. Let's say you take u1 to be 1, 0 and you take u2 to be 1, 1. Okay. Now let's try to find a1 and a2 such that a1 u1 plus a2 u2 gives us 0. Okay, we'll try to find such a1 and a2. a1 u1 plus a2 u2. We want such a1 and a2 such that this thing is 0. Okay, let's put it over here. a1 1 0 plus a2 1 1 is 0. What does this imply? That a1 plus a2, and in the second term we have only a2, is 0. Okay, what does this mean? If we compare just the second quantity over here, this means that our a2 must be 0. Okay, and now if we put this in the first equation that we get, what we would get is that a1 plus 0 is equal to 0. This implies a1 is equal to 0. So what does this mean? This means that the only way we can make this a1 u1 plus a2 u2 to be 0 is by taking a1 equal to 0 and by taking a2 is equal to 0. But for our linear dependence condition, what we wanted is that at least one of these a1, a2, an's should be non-zero. But because we got both of them to be 0, so this vector u1, u2 is linearly independent. Okay. Is this clear to everyone? Any doubt in definition of linear dependent and independent? If there is, I can again try to explain it to you if you have. Okay. So I hope the definition was clear, but again to reiterate that you will try to find such a1, a2, an such that summation an un is 0. If you find such an an such that not all are 0, then that leads to linear dependence. If you find only an such that your all an's are 0, then it is linearly independent. Okay. Okay, let's see one more thing. Then we'll move to the questions definitely. Okay. I hope this thing was clear to everyone. If it is not clear at any moment, please stop me and ask. Okay. Now, if you look at this particular equation over here, so what it was? It was a1 times 1 0 plus a2 times 1 1 is equal to 0 comma 0. Now, if you want to write this thing in terms of matrix, the way we discussed like how a matrix multiplication works, you can write this as first column, and then this gets multiplied by a1, the first element that it is getting by this, and next is 1 1 multiplied by a2. You can look at it also that it is a1 plus 1 times a2. Otherwise, you can just pick the first row, like first u1, and you can place it as first column. Okay, and then you can place the second vector as second column, and you will try to find a1, a2, right? And then you equate it to 0 comma 0. Now this is your system of linear equation that you have been solving in first 2 weeks. Okay. Okay. Now, when do you have a unique solution for this system of linear equation? Let's say this is your matrix U, this is your vector. Let's use our general notation only. This is your matrix A, this is your matrix X, and this is, let's say, 0. Okay. When did we have unique solution for this kind of equation when you had 0 on the right hand side? So when your A inverse existed, or in other words, your A matrix was full rank, then your this unique solution existed. So if only one solution exists for this kind of equation, what is that solution? That must be A1 is equal to 0 and A2 is equal to 0. 0, 0 is the case when you have unique solution in case of homogeneous solution. So one simple way to check if your vectors are linearly independent or not, so rather than going everything, what you can try to check is, like, if you have, let's say you want to check whether your vectors u1, u2, un are linearly independent or not. Okay, what you can try to do is, first of all, you will write u1 as your first column, u2 as your second column, and so on till un. Okay, now if this matrix is invertible, okay, then it is a full rank and hence unique solution. Just one thing that you should take care is that this is only for n cross n matrices. Like when you have same dimension and same number of vector, then you can use this trick. In most of the cases, you will get this kind of situation only when you have same number of dimension and same number of vectors. Okay. So how do you check whether a matrix is invertible or not? If you recall your school days, one way to check that was if determinant of that matrix is not equal to 0. So to summarize, what you can do is you can just write this thing as a matrix and then find its determinant. Okay, if it is a square matrix, most important thing, then if your determinant is equal to 0, then those vectors are linearly dependent. If it is not 0, then your determinant is, then your vectors are linearly independent. Okay, now let's see this thing to the two examples that we took before. First example that we took was 1 1 minus 2 comma minus 2. Okay, so u1 was 1 1 and u2 was minus 2 comma minus 2. Now what did I say? We will write it as a matrix. Okay, so first is 1 1, first column, second is minus 2 comma minus 2. Now if we take its determinant, what it is? It is 1 comma 1 into minus 2 minus 1 into minus 2. So this gives you 0. And what we obtained earlier also was that these vectors are linearly dependent. Okay. Again, for the second case, it is pretty simple. It was 1 0 1 1. So if you take its determinant, it's 1 minus 0, which is 1, which is not equal to 0. So these vectors are linearly independent. Okay. Now I'll leave this thing to you. I'll like take a pause for 1 minute or two for you to solve, you guys to solve. Try these vectors. So we have a set of 4 vectors over here, 1 2 3 4. They have asked us whether this set is linearly independent or linearly dependent. Okay, so just construct a matrix and check its determinant if it is 0 or not. I'll wait for 2 minutes for your reply to see whether it's independent or dependent. See, these are tutorial sessions. If you will like write it down and try on piece of paper, then it will be more beneficial for you. So you can just start writing it as a matrix whose first column is first minus 4, 2. Next is 2, 2, minus 4, 0, 1, minus 3, 2, minus 4, minus 1, 0, 1, 0. You need to find its determinant. Either you can calculate determinant using the long method, or you can try to reduce it to some reduced form using your elementary operation, so that you easily get the like this determinant. You can try to row reduce it so that you can easily find your determinant. I'll wait for one of you to type whether it's LI or LD. So you can try this row operation, that your R3 goes to R3 minus R2, sorry, make it plus R2 plus R1. So you can try this operation and see if you get something out of it. So your first row remains as it is, second row remains as it is. Now if you go to third row, I have made third row to be the sum of these three rows. So 1 plus 3 is 4, minus 4, it goes to 0. This is 2 plus 2, 4, minus 4 goes to 0. This is 1 minus 3 minus 2 plus 2 is 0. This element is again 0. Okay. So this is 2, 0, minus 4, 0. Now, because one of the rows is 0, okay, so the determinant we would get is equal to 0. Right? If in any matrix you have one of the rows or column to be 0, then the determinant that you get is 0. So this set of vectors is linearly dependent. Okay. Now we'll go to, I think I should go to a simpler example. Okay, let's try this one. Then we'll go to the matrix one so that you guys can also try. This is also similar. This is 4 vectors belonging to R4. So you just need to check whether it is independent or dependent. So again, I'll write it as a determinant. You guys also please solve along with me. 1, 0, 0, minus 1, 0, 1, 0, minus 1, 0, 0, 1, minus 1, 0, 0, 0, 1. Okay. So we have one row in which we have only one non-zero entry. So if we try to evaluate along this, what would we get the determinant as? 1 into, so we hide this row and we hide that column and we hide this row, then we get 1 into determinant of 1, 0, 0, 0, minus 1, 1, minus 1, 0, 1. What you would get, again I'm evaluating along this particular row, so I would get something like 1 into, so this is 1, we hide this is 1 minus 0, and rest everything is 0. So you get determinant to be 1. which is definitely not equal to 0. So this set over here we had is linearly independent. Any doubt in this? Shankar, was it clear to you?
Yes, sir.
Jaya, are you there? Was it clear for you? I'm not sure whether she's here. Okay. I'll get back to this example at the last, but let's take some more useful examples. Okay. So here is a theorem. You can take it as a example that we are going to solve. So we have to prove this thing. We have to prove this thing. Okay. I'll try to go step by step. So let's see what it is asking us to prove. It says, let V be a vector space and S1 is a subset of S2 and is a subset of a V. So we have V as a vector space, and let's say this is V, and we have two smaller sets. One is S2 and inside it is S1. Okay. It is saying that S1 is linearly dependent. Okay. So this inside set, this is linearly dependent. It is asking us to show that this outside set is also linearly dependent. Okay. Now, if we get back to our definition of linear independence, so you call a set S as linearly dependent if you have some vectors u1, u2, un such that you find such scalars. Okay. Right. So let's start from what is given to us. Okay. We are given that S1 is linearly dependent, and we have to prove, and also we are given that S1 is a subset of S2, and we have to prove that S2 is linearly dependent. Okay, let's go through the proof now. Now, if we look at the uh, definition of linear dependence, it is given to us that S1 is linearly independent. So, what does this mean? There exists, let's say U1, U2, Un, all belonging to S1, such that we have alpha 1, alpha 2, let's say A1, A2 only to avoid any confusion. So we have A1, A2, An, all of them, or we can say such that at least one of them is non-zero. Okay. And A1 U1 plus A2 U2 plus An Un is 0. So because S1 was linearly dependent, we can write this thing for S1, right? Now, as you observe that S1 is a subset of S2, so if U1, U2 and Un belong to S1, then what does this mean? That our U1, U2, Un belong to S2, which is quite obvious, right? Because S2 is a subset, superset of S1. Now, because this belongs to S2, and we already found such pair, so that A1 U1 plus A2 U2 plus An Un is 0, what does this both imply? That S2 is linearly dependent. Is it clear for you, Shankar? I hope it is clear, the proof. Okay. So now I go to the next, I would say a corollary, but let's call it also as an example. So we need to prove this thing. Okay. So in order to prove this thing, what we can see is what we have been asked first. Okay. So we are given that we have a vector space again V, and we have two of its subset nested together. So this is S1, this is S2, this is whole of V, and we are given that this S1, oh no, right now we are given the converse so we are given that this set S2 is linearly independent. So we are given that this is linearly independent. We have to prove that S1 is linearly independent. Okay, let's begin that. So we are given that S2 is Li, okay, and S1 is a subset of S2. Now, to prove we have to prove that our S1 is linearly independent. Okay, we'll tackle this one using contradiction. Okay, so we'll begin by assuming, okay, let us assume that S1 is linearly dependent. We assume the opposite of what we have to prove, right? We assume that S1 is linearly independent. Then by the previous you can say theorem or the example, if S1 is linearly dependent, then what that would that mean is that this would imply that S2 is linearly dependent. But what are we given? That S2 is linearly independent. So this contradicts our given fact, and hence S1 is, hence our, we can say that hence our assumption is incorrect, and S1 is linearly independent. We'll try to solve these examples towards the end because these examples would take time, and whatever time is left towards the end, we'll try to solve these examples. Before that, let's move to something called as rank nullity theorems. Okay. So I have defined these things before, but just to make sure that all of us are on same page, I'll just define what is rank and nullity of a matrix A. Okay. Let's say A is a M cross N matrix. Then rank is defined as number of pivot element in row echelon form of our matrix A. So when you row reduce or reduce it to echelon form, the number of pivot element that you get, that is the rank of your matrix. Okay, and yeah, so and you talk about nullity. Nullity is dimension of your null space. Okay, now what do you mean by null space over here? So for a matrix A, for A, null space of A is defined as set of all x such that Ax is equal to 0. Okay, so this is something which is known as the null space of a matrix A. So if you look at the basis for this vector space, then its dimension is something that is called as the nullity of a matrix. Okay, now what does this rank nullity theorem state? Rank nullity theorem states that, so if you take number of columns of A, then it can be broken down into two parts. First is rank of A and second is nullity of A. We can take a short example to show this thing. I'll take a very short example. So let's say our matrix is something like 1, 0, 1, 0, 1, 1, and let's take it to the 2, minus 1, 1. Okay, this is our matrix. Let's try to row reduce this matrix. Okay. So we want to make this entry to be 0. We want this entry to go. So what do? We do R3 goes to R3 minus 2 times R1. Does this become? This becomes 1, 0, 0, 0, 1 minus 1, 1, 1 minus 1. Okay. Now you can see that this thing that I've highlighted in green has become a pivot element over here, right? Now this is a candidate for next pivot element. We want everything below that to be 0. So you want this thing highlighted in sky blue to go to 0. How can we make it go to 0? We can do the operation R3 goes to R3 plus R2. Okay. So what do we obtain with this? We get 1, 0, 1, 0, 1, 1, 0, 0, 0. So how many pivot elements do you see? You see 2 pivot elements over here. Okay. So what is rank of A? It is 2. Okay. Now if you look at the null space, what we want Ax to be 0, or this is same as REF of A into x to be 0. So what we want eventually is, we want 1, 0, 0, 0, 1, 0, 1, 1, 0 times x1, x2, x3, let's say, to be 0. Okay. So you see that the first row gives you x1 plus x3 as 0. Second row gives you as x2 plus x3 as 0. Okay. So now you see that you have three variables and you have only two linearly independent equations. So what you can do is you can see that one of the variables is free. You can choose that free variable out of your choice. I'll choose x3 over here as a free variable. Okay. If I take this to be free, let's say I take x3 to be a, then what is my x2? x2 is minus a, and similarly x1 is minus a. So any element of the solution space would look something like minus a comma minus a comma a. Okay. So if you look at this carefully, we may have one choice to make over here. So if you want to obtain different elements of solution space, you have one choice to make, that is your a. So dimension of a subspace is nothing but number of choices that you have to make. So as you have one choice over here, so dimension of null space is equal to 1. Now if we re-verify our rank nullity theorem, what does this say? That rank of A plus nullity of A should be equal to number of column. Okay. So rank we obtained as 2, nullity we obtained as 1, and if you look at the matrix, we have 3 columns. Right. So this thing is verified. Well, with the help of an example, you can look into the proof. You will get it in chapter 2 of Friedberg book. Okay. Now let's solve some questions based on our rank nullity theorem. Okay. So first question is that there exists a 3 cross 3 matrix. So we have to answer whether these statements that are given are true or false. Okay. So the first statement says there exists a 3 cross 3 matrix such that rank of A is equal to nullity of A. Okay, let's say if this kind of matrix existed, so rank of A plus nullity of A is equal to 3. Okay, now as these two are equal, let's replace it by rank of A. This is 3. This would imply that rank of A is 3 by 2. But this rank and nullity are integers. Nullity are always integers. We can't have fractions in case of rank of a vector space. So this can never hold. So this statement is false. Okay. I hope it is clear. Now moving on to the next. Now let's say if A is a 4 cross 3 matrix, okay, and the equation Ax is equal to 0 has no non-zero solution. So no non-zero solution means nullity, let me use capital N only for nullity from now onwards. So nullity of A is 0. Okay. Then it says that rank of A is 3. Okay, let's see. Now what we had, number of column, which is equal to 3 in this case, okay, is equal to rank of A plus nullity of A. We are given that nullity of A is 0, so this means 3 is equal to rank of A. So this thing x whatever is given over here. So this is true. Okay. Let's look at next true or false question. It says that there is a linear transformation T such that its kernel is 0. Okay, there are a few new notations over here. So I'm sure Professor Rana will have this T converted to some matrix in later part of the course. Okay. But right now what I'll say about this thing is that if T is from R4 to R3, okay, then the corresponding matrix has size. So this is R4 to R3. So it will take elements from R4. So it's 3 cross 4. Okay. So basically the relation that you get is that P of x is equal to A of x. So if your x is from R4, so your x is 4 cross 1 in this case. So you want your A to have like 4 columns. Okay. Now we are given over here that this transformation or a matrix A has size 3 cross 4 and its kernel is 0. Okay. Is it possible or not? It is asking. Okay. Now, as the matrix is 3 cross 4, right? This is 3 rows. So, how many pivot element it can have at maximum? Okay. So, max number of pivot element is equal to 3. So, the maximum rank then this matrix can have, maximum of rank of A is 3, right? So, rank of A is always less than equal to 3 because you can't have more than 3 pivots if you have only 3 rows. Okay. Now, according to rank nullity theorem, the number of columns, which is 4, should be equal to rank of A plus nullity of A. So if this is less than equal to 3, then your nullity of A must be equal to greater than equal to 1, right? But what they are claiming is that its kernel is 0. Kernel is nothing but the null space. Okay. So if the dimension of, if our null space is 0, or the nullity is 0, then this thing does not hold, right? So this fact over here is indeed false. Okay, let's see this example. It says that there is a 3 cross 6 matrix, okay, whose kernel is 2-dimensional. Again, as number of row is 3, then rank of A must be less than equal to 3. Okay, and 6 is equal to rank of A plus nullity of A. What does this give us? This gives you that nullity of A should be greater than equal to 3. But they are saying that it is of dimension 2. So again, this fact is also false. Okay, let's get to the next question. Let's say if your A is 3 cross 5 matrix whose kernel is two-dimensional, then this system has infinitely many solutions. This is what it is asking. Okay, so let's see how can we tackle this kind of question. So what we are given, that we have some matrix A which has 3 rows and 5 columns, and if we include, let's say, our augmented matrix, so we have one more column corresponding to this B. Okay, this is A and B. Okay, now it says that the kernel has dimension 2, or nullity of A is 2, right? If your nullity is 2, what does this give you about this, about its rank? So it tells you that 5 is equal to rank of A. 5 is your number of columns that I picked from here, plus nullity of A. So this gives you rank of A is equal to 5 minus 3, okay, which is your 5 minus 2, I'm sorry, which is 3. Okay, so rank of A is 3. What does that mean? That you have some pivot element in 3 rows. Okay, so in 3 rows, that means you will have pivot element in all 3 rows, maybe here, or you can have somewhere here, but you'll have pivot element in all 3 rows. Okay, so what does that mean? That means that rank of A is equal to 3 is equal to rank of A augmented with B. Okay, and which is equal to 3, which is strictly less than number of variables, because my number of variables is equivalent to the number of columns, which is 5. Okay, so what kind of case does this give? This gives you infinitely many solutions. Okay, if you remember that if you have rank of A is equal to rank of A augmented B, which is strictly less than number of variables, then you have infinitely many solutions. So no matter what B you had over here, you would have infinitely many solutions. Okay, let's go to the next question. It says that there exists a matrix whose image is R5. Okay, now image being R5 means if you take the set AX for all x belonging to, in case, R4 over here, because entries are coming from R4, then this space is called as the image space for the matrix, A. Okay, so or in other words, rank of A is the dimension of image space of A. So we talked about nullity of A being the dimension of null space of A. Now the rank of A can also be defined as the dimension of image space of A. Now if you look at rank nullity theorem, in this case, what does that give? It gives you that 4 is equal to rank of A plus nullity of A. Now because all these quantities are greater than 0, this nullity of A should be greater than equal to 0. This is also greater than equal to 0. This gives you what does this gives you? This rank of A should be less than equal to 4. That's the only possibility. But what it is asking is that rank of A should be equal to 5. Okay, which is not possible. So this statement is also false. Okay. Just wait a minute. Give me a minute. Yeah, I think this is done. This is better now. So now we'll deal with these questions that we left related to linear independence. Okay. I hope it was this rank nullity theorem was clear to everyone. So among those who joined late, I think you joined at 7. So if you guys have any doubt with the rank nullity theorem, or if you want me to repeat, I can repeat it. So, but you will have to ask like if you want me to repeat or not. So I can go in Hindi also if you want, if you understand it better in Hindi. I think Ashutosh and Jyoti joined late. So if you want me to go through this rank nullity theorem again, I'll be happy to do so.
Hello.
Hello. Hello, you are
Sir, I
audible.
have already joined, but network issue.
Okay. So you know what is rank nullity theorem, you understand it?
Yes, sir.
Okay. Then I'll go to solving these questions on linear independence. Okay, you can mute yourself. Thank you. Okay. So here we are given three matrices from the set of two matrices of size 2 cross 3, and we have been asked whether this set of matrices is linearly independent or not. Okay. So now if you see, we can't use our matrix trick like writing this in form of matrix and then solving. We will have to use the definition of a linear dependence and independence to check whether this is linearly independent or not. Okay. So let's go that way. Let's say A1 times, we'll name this matrix as M1, M2, and this as M3. So A1 M1 plus A2 M2 plus A3 M3 equal to 0. Okay. Now if you write the first element using this, let's see what we obtain. We obtain that A1 plus A2, okay, A1 minus 3 A2 minus 2 A3 equal to 0. Second entry gives minus 3 A1 plus 7 A2 and then this entry would give me plus 3 A3 equal to 0. This is minus 4 A1. Okay, I'll take the third entry only. So this is 2a1 plus 4a2, and this would give me plus 11a3 equal to 0. So I can write 3 more equations using these 3 entries. This is 1, 2, 3. But because I have 3 variables and I already have 3 equations, so we can try to solve using this only. Okay, and then we will try to see if that thing holds for other entries also or not. There is a possibility that it might hold. There is a possibility it might not hold. So rather than solving all the equations, we can solve first for 3 and then see whether it holds for others also. So let's write this in form of a matrix. This gives me 1 minus 3 minus 2, okay, minus 3, 2, 7, 4, and this entry is 3, 11. Okay. So one thing I'm seeing over here is that if I combine these two entries, I'm getting this middle entry minus 3. So 1 plus 2 is 3. But that same thing is not holding over here, so probably of no use. Yeah, 1 minus 3, 2, minus 3, 7, 4, minus 2, 3. Okay, so we'll go the normal way. Yeah, we'll go the normal way. Try to reduce it to row echelon form. Am I audible? First of all, am I audible to you guys? I think I am. Okay. Yeah. So, thank you, Ashish. So we had this thing. We want to make these two entries are 0. So we can go the usual way. We can take R2 as R2 plus 3 times R1 and R3 as R3.
Sir, hello.
Hello.
Determinant value of this matrix is 0. So dependent.
Yeah.
LD.
Yeah, you can say like that also. So, but what we want to do is we want to find values of A1, A2 and A3. Okay. Now, why we want to find A1, A2 and A3 and why not only we are looking at determinant is because we will get 3 more equations from the rest of the terms. Okay. So, it is possible that you get A1, A2 and A3 that satisfies for this first 3 entries. Okay. But we also want to check whether the same A1, A2 and A3 satisfies for the rest of them also or not. Okay. So that's why I'm solving this equation rather than looking at just the determinant. Okay. So we will go R3 minus 2R1. Yeah. So what we obtain? We obtain this as 1, 0, 0. Now we added 3 times to it. So this is minus 3. This we get as minus 2. We have subtracted, so this goes to 10. Okay. So this is minus 2. Now we have again added 3 times, that is minus 6. So this is minus 3 and this thing is 15. Okay. Okay. So now what we can do is we want to make this entry as 0. So we can add R3 goes to R3 plus 5 times of R2. What does that give us? 1 minus 3 minus 2, 0 minus 2 minus 3, 0, 0, 0. Okay. So we have now two relationships with us. So this means we'll get some non-zero A1, A2 and A3, right? Now, what we have minus 2 A2 minus 3 A3 is equal to 0, and 1, this is A1 minus 3 A2 minus 2 A3 is equal to 0. Let's take A3 to be some S. Okay, then what does this give? That A2 is minus 3 by 2 times of S. Okay. Or okay, let's take this only. And then if we obtain from here, then A1 is minus 9 by 2. This goes minus 9 by 2 S minus 2S. This implies that A1, this is 0, so this implies your A1, just wait a minute. Yeah. So your A1 is 2S minus 9 by 2S, which is A1 is minus 5 by 2S. So the solution space looks something like minus 5 by 2S, comma, minus 3 by 2S, comma, S. So if we take our S is equal to 2, just we want one A1, A2, A3, such that all of them are non-zero. Let's take S is equal to 2, then what do we obtain as? Minus 5, comma, minus 3, comma 2. Now let's check this in rest of the three equations. So this is minus 5 times 4 plus minus 3 times, sorry, this is minus 5 times minus 4 plus minus 3 times 6, okay, and then last is 2 plus 2 times minus 1. What do we get? This is 20 minus 18 minus 2. We get 0. Now for the second position, what we can similarly do? This is 6 minus 6, which is again 0. Okay. Now for the last one, from here we get minus 20. From here we get plus 21. Wait, we get 5 4s are 20. Yeah. From here we get 21. And from here, let me write it down. So from here we get 5 into minus 5, which is minus 25, plus minus 7 into 3, minus 3, plus 2 into 2, this is minus 25, plus 21 plus 4, which gives us 0. So these three matrices again turns out to be linearly dependent, as you pointed out, but this was just to confirm whether it is actually linearly dependent or not. So we should not trust. Yeah. You are saying something.
Hello,
Yes.
hello.
Hello.
Sir, please explain again.
Okay. See, you are comfortable with Hindi?
Yes, sir.
हाँ देखो, हम मैंने क्या कोशिश किया कि अब हमें इन तीनों का लीनियरली डिपेंडेंट चेक करना था है कि नहीं। तो हम लोग अगर इसको इस फॉर्म में लिखें a1 m1 प्लस a2 m2 प्लस a3 m3 इक्वल टू 0, और अगर हमें ऐसा कोई a1 a2 m3 मिल जाए जिसमें कि सारे टर्म्स जीरो ना हो, यानी हमारा कुछ a1 नॉन जीरो हो, a2 कुछ नॉन जीरो हो,
यस
या
यस।
तो लीनियरली डिपेंडेंट हो जाएगा। ठीक है, तो हम अब इसको सॉल्व करना शुरू किया हम लोगों ने। तो पहले से क्या आएगा हमारे पास, a1 - 3, यहाँ से देखो a1 इंटू ये m1 -3 a2 -2 a3,
-2 a3।
है
यस।
ना। अब ऐसे ही सेकेंड वाले टर्म से भी इक्वेशन से हमने निकाल लिया -3 a1 +7 a2 +3 a3 इक्वल टू 0। वैसे ही लास्ट वाले से भी निकाला 2 a1 +4 a2 +11 a3 इक्वल टू 0, और उसको फिर हम लोगों ने सॉल्व किया था। ठीक है, अब पर हमें करना क्या चाहिए था कि हमें ये वाले भी टर्म्स वेरीफाई करने चाहिए थे कि जो बाकी जो तीन बचे, है ना, वो भी लिखने चाहिए थे ना। -4 a1 +6 a2 प्लस ये -a3 आएगा 0। तो ऐसे कितने इक्वेशंस बन जाते हैं हमारे पास, 6 इक्वेशंस, है ना। तो छः इक्वेशन को साथ में सॉल्व करते तो टाइम लगता, मैट्रिक्स बड़ी बन जाती। तो मैंने क्या सोचा कि मैं पहले तीन
वेरी
इक्वेशन,
कॉम्प्लेक्स ही थी।
हाँ, सो आई सॉल्व दिस फर्स्ट 3 इक्वेशंस फर्स्ट। ठीक है, तो तीन का जो सोल्यूशन आया उसको मैंने पुट करके बाकी तीनों इक्वेशन में देखा कि सेटिस्फाई हो रही हैं या नहीं हो रही हैं। ठीक है, अगर वो सेटिस्फाई कर रही हैं तो वो a1 a2 सबके लिए सेटिस्फाई कर गई, और वो कर रही थी सेटिस्फाई। मैंने एक यहाँ पे लेके देखा तो एक सोल्यूशन इसका ये वाला। ठीक है, तो इसलिए लीनियरली डिपेंडेंट हो गई।
सर
हम्म, हाँ बोलो।
ये जो लास्ट में वो थोड़ा सा आप और नीचे स्क्रॉल कीजिए।
हाँ हाँ
या ये -2 a2 -3 a3 इज इक्वल टू 0, एंड सेकेंड इक्वेशन a1 -3 a2 -2 a3 इज इक्वल टू 0।
हम्म
देन फ्रॉम फर्स्ट इक्वेशन बी रिलेशन बिटवीन a2 एंड a3।
हम्म। तो मान
फिर
लो,
उसको हमने पुट कर दिया
हाँ हाँ
सेकेंड इक्वेशन में।
हाँ,
यहाँ से डायरेक्ट a1 a2 a3 का वैल्यू कहाँ से आ गया?
अच्छा देखो,
तो इसका
अभी,
कोएफिशिएंट आपने लिया था।
हाँ देखो क्या कर रहे हैं हम लोग। अभी हम लोग के पास रिलेशन क्या आया था कि a2 इक्वल टू
a2 इज इक्वल टू
-3/2 a3,
यस
है ना। और अगर हम लोग सेकेंड में a2 में भी a3 की वैल्यू डाल दें तो क्या आएगा, a1 इक्वल
हाँ
टू -5/2 a3। ठीक है, अब यहाँ पे देखो हमारे पास इक्वेशन कितने थे, दो, है ना। इक्वेशन दो ही थे हमारे पास ये दोनों। उससे हमें
यस सर
कितने वेरिएबल के बारे में जानना था, 3 वेरिएबल्स के बारे में। ठीक है, तो इसके ऐसे केसेस
यस
में इनफाइनेटली मैनी सॉल्यूशंस आता है ना। मान लो तुम्हारे पास ऐसा इक्वेशन हो x + y = 1, है ना। तुम y की वैल्यू कुछ भी रखोगे,
यस
मान लो 0 रख दिया तो एक सोल्यूशन आ गया तुम्हारे पास 1, 0। ठीक है, और फिर कुछ और रख दिया, अगर मान लो y में तुम -1 रख दो तो यहाँ 0 आ जाएगा। तो ये पूरा लाइन बनता है ना,
यस।
है ना। तो ऐसे ही यहाँ पे भी हमारे पास एक इक्वेशन कम थी, तो यहाँ भी इन्फाइनेटली मैनी सॉल्यूशंस आएंगे। तो मैंने क्या किया कि a3 में एक वैल्यू ऐसे ही ले लिया, a3 को क्या ले लिया मैंने, 2 ले लिया।
यस
तो फिर हमारे पास ये सोल्यूशन आ गया। a3 को
ओके।
2 लेंगे तो a2 आ गया -3, और a1 आ गया -5। ऐसा क्यों
ऐसे
किया
कुछ
हमने,
भी वैल्यू खुद से असाइन कर सकते हैं ऐसा?
आ, ऐसा इसलिए किया क्योंकि हमें लीनियरली डिपेंडेंट दिखाने के लिए तो एक ही कोई a1 a2 a3 चाहिए ना। तो वो हमने
यस
एक पुट करके चेक कर लिया। पर कोई अगर तुमसे पूछे कि इसका सोल्यूशन स्पेस क्या होगा तो तुम फिर उसको इस फॉर्म में लिखोगे, इसी फॉर्म में कि ऐसा लिख
ओके
सकते हो कि -5/2 a3,
ओके
कॉमा 3/2 a3, और यहाँ पे a3, ऐसा लिखोगे फिर। और a3 क्या
ओके
है,
सर।
3 वेरिएबल। ठीक है,
सर ये फिर आपने माइंड में कहाँ से आएगा कि A3 का वैल्यू 2 ही पुट करना है?
वो तुम कुछ भी लोगे ना तो वो लीनियरली डिपेंडेंट आ जाएगा। मैंने 2 इसलिए लिया क्योंकि इसके डिनोमिनेटर में 2 था ना, तो वो कैंसिल हो जाता तो फिर
अच्छा,
कैलकुलेशन
तो
थोड़ा
2 से
आसान हो
कैंसिल
जाता।
होके -2, ओके
हाँ,
ठीक है।
तो कैलकुलेशन थोड़ा आसान होता, कुछ भी लोगे तुम।
देखो कैलकुलेशन इजी करने के लिए और फिर वो इंटीजर टाइप में आ जाए
हाँ,
तो।
इसीलिए
हाँ
वो
ठीक
तुम
है।
कुछ भी लोगे तो सोल्यूशन वो लीनियरली डिपेंडेंट आ जाएगा।
ओके।
सो आई थिंक जो लेट ज्वाइन किए हैं, यू नो दिस थ्योरम कि अगर हमारा वेक्टर स्पेस है कोई v, ठीक है, एंड वी हैव S1 सबसेट ऑफ S2, और हम लोग प्रूफ करना चाहते हैं कि अगर हमारा S1 लीनियरली डिपेंडेंट हो गया, सो वुड आर S2 भी ऑल्सो लीनियरली डिपेंडेंट और नॉट। तो मान लो S2 बाहर वाला सेट है और S1 अंदर वाला सेट है। अगर अंदर वाला लीनियरली डिपेंडेंट हो गया तो बाहर वाला भी लीनियरली डिपेंडेंट होगा। ये एक थ्योरम है वैसे तो, बट डू यू नो हाउ टू प्रूव दिस?
नो सर।
ठीक है, मैं इसको करता हूँ। विच लैंग्वेज आर यू मोर कंफर्टेबल इन, हिंदी और इंग्लिश?
सर बहुत।
ठीक है, तो आई विल कंटिन्यू इन इंग्लिश ओनली सो दैट मोर पीपल अंडरस्टैंड। ओके, देखो फर्स्ट लेट्स सी लाइक हम लोग को दिया क्या हुआ है। ठीक है, लेट्स सी व्हाट्स गिवन टू अस। सो वी आर गिवन first of all is that S1 is a subset of S2, okay, and we are given that S1 is linearly dependent। ठीक है, अब linearly dependent का what is the definition of linearly dependent? कि we will have some vectors, let's say u1 u2 un, which will belong to S1, and we will have some
वेक्टर्स
scalars,
वैल्यू आर इक्वल टू 0।
हाँ, some scalars an, such that not all of them are 0। ठीक है, and we will have a1 u1 plus a2 u2 plus an un is equal to 0। Now, if my vectors u1 u2 to un belong to S1 and S1 is a subset of S2, what does this mean? This means that my vector u1 u2 un will also belong to S2। Okay, now because my these vectors belong to S2, and if I pick same like this a1 at, now if I take same a1 a2 an, then what would it give me? Again it would give me that a1 u1 plus a2 u2 so on, an un is 0। So what this mean? That these vectors are linearly dependent. That would mean this my set S2 is also linearly dependent। Is it clear? Okay, here are some questions on this linearly dependence and independence. So I'll try to solve some of them. Okay, probably related to polynomials we have not solved any, so let's take the third one first। Okay, so we have, let's say this is p1, this is p2, this is p3। Okay, so what we want a1 p1 plus a2 p2, this is c part that I'm solving, plus a3 p3 to be 0। Okay, so let's write all the terms related to x cube together, all the terms related to x squared together, and so on. So what we would get is a1 minus 2a3 into x cube. If we look at, okay, so I think I went to different example. Sorry. Yeah. So what we would get is a1. Then we have this x cube term in third one. So yeah, this is x cube here and then x cube here. We don't have any x cube in the second one. So a1 plus a3 x cube plus 2a1 minus a2 minus a3 x square plus, this is 3 times, right? 3a2 plus 2a3 x plus a2 minus a3 is equal to 0. So now for a polynomial to be 0, like the coefficient of every degree must be equal to 0, right? So if we start from the last, what it would give us is a2 minus a3 equal to 0, or that means a2 equal to a3. Okay. Now if you go to the first term, what does that give us? This gives us that a1 plus a3 equal to 0, or a1 is equal to minus a3. Let's see if whatever conditions we got from these two are satisfied in other two. Okay. So let's put these values in these equations. So we obtained 2a1. Let's write everything in terms of a3. So this gives us minus 2a3 minus a3 minus a3 equal to 0. What does this give mean? That minus 4 a3 is equal to 0, or a3 equal to 0. Now if my a3 is 0, then my a1 also becomes 0. Then my a2 also becomes 0. What does this mean? So the only way to get a1 p1 plus a2 p2 plus a3 p3 to be 0 is when your a1 is equal to a2 is equal to a3 is equal to 0. So that's why these three polynomials are linearly independent. Okay. So we can try one more example. So we are given three polynomials as x cube minus x plus 2x square plus 4 minus 2x cube plus 3x square plus 2x plus 6. Okay, let's take this down. Okay, let's call it P1. This one as P2 and this one as P3. So A1 P1 plus A2 P2 plus A3 P3 equal to 0. what does this mean is, let's take again the coefficients together. So this means a1 minus 2a3 x cube plus 2a2 plus 3a3 x squared. Okay, and if you look at the x term, this is minus a1 plus 2x, so this is 2a3 times x plus, if you just look at the p2 now, this is 4a2 plus 6a3, which is equal to 0. Now the first term gives us a1 is equal to 2a3. Okay. Now the second one gives us 4a2 is equal to minus 6a3, or this implies that a2 is equal to minus 3 by 2 of a3. Okay. Let's put it in this equation right here. So let's put it in this equation. Let's see if we can obtain something. So this equation over here also gives us 2a2 is equal to minus 3a3, or a2 is equal to minus 3 by 2a3. So we don't get any new information. Okay. Now, if we now see at this equation, what does this say? This one say that minus a1 plus 2a3 equal to 0, or a1 is equal to 2a3. So whatever we are getting, so the solution is of form 2a3 comma minus 3 by 2a3 comma a3. Okay. So if we take a3 to be anything now, let's say we take it to be s, then we get 2s minus 3 by 2s comma s. So we have a non-zero solution for us, and hence this set of polynomials are linearly dependent. Okay. We can try others also similar way, and I have covered one example of each type. So I think this is what I prepared for today, and we will call it a day. Any doubt for anyone? Anybody wants to ask anyone anything? If not, then I'll probably end this session here.